All right, honors, probability statistics. This is section 7.5, dealing with the central limit theorem. And it's going to look a lot like 7.3. All right, we're going to actually make a comparison with 7.3 that will hopefully show you the difference between the two. But the math, the work is exactly the same. Okay, we have to manipulate one of the numbers. Okay, but you're still going to be doing a greater than, a less than, and an in between. And here's the difference in a sense. This is what you just took a test on. A raw data piece. A raw data piece X. Less than or equal to some value. A raw data piece X greater than or equal to some value. And a raw data X in between two numbers. That's what you just took a test on. The difference between 7.3, which is this is 7.3. That's pretty ugly 7.3. 7.3. And 7.5 is this. And I'll do it in red. Instead of just X, it's going to be the mean. We still have less than a number. Instead of just X, we have the mean of X greater than some number. And again, X bar in between two numbers. So 7.5 is not going to deal with raw data. It's going to deal with the mean of a set of raw data. Okay? All right, guys, that is the end of section 7.5. As you see, it's very much like 7.3. So real quick, I just wanted to show you the definition. Look, standard error is the standard deviation of a sampling distribution for the X bar sampling. So a standard error is still a standard deviation. It's just you're taking the original sigma that's given to you and dividing by the square root of n. Okay, special name. So here's a sample, an example in its entirety. A certain strain of bacteria occurs in all raw milk. Let it be a millimeter of milk. Let X be a millimeter of milk. The health department has found that the milk is not contaminated if X has a distribution that is more or less mound-shaped and symmetrical. So they're kind of telling you that it's normal. The mean of the X distribution, which we know is mu, is 2,500. And the standard deviation is 300. That's sigma. All right, remember, this is X. So right now they're talking in terms of 7.3. In a large commercial dairy, the health inspector takes 42 random samples. Oh, so N is 42. So far, the central limit theorem is met. At the end of the day, the bacteria count in each of the 42 samples is averaged, that means mean, to obtain a sample mean of bacteria, which we call X bar. We are now at 7.5. They average it. Whoops, gotta go to the next page. So, assuming the milk is not contaminated, what is the distribution of X bar? So when you see that question, what is the distribution of X bar? That means you're using the central limit theorem, especially when n is 42, which is a number greater than 30. So here we go. The mean of X bar is going to be same as the mean of our problem, which is 2,500. The sigma, the standard deviation of the means, since we do have the central limit theorem, is now going to be 300 divided by the square root of n, or the square root of 42, which is 46.3. This is new. Now we need a question. Assuming the milk is not contaminated, what is the probability, so they're asking for a probability, that the average, that means X bar, bacteria count X bar for 1 day is between 2350 and 2650? Come on, guys, that's pretty straightforward. So it's in between 2350 and 2650. There's our set little formula. This is our 2350 and our 2650. There's our mean. There's our standard error. Here's the work. 2350 minus the 25 divided by 46.3. That's what we yield. Do the bigger number. That's what we yield. Don't worry about them being the same numbers. The book does that for some reasons. I never give the same values. Look up the big number and get 9994. Look up the small number, get 0006, and subtract. So guys, if I use the word chance, there's a 99.88% chance that the bacteria level in the sample of milk is going to be between 2350 and 2500. Done. Guys, it's the exact same thing as 7.3. The only difference is instead of given just X, you are given X bar. They're going to use the word average in the question. Okay? But the math behind it is exactly the same as long as you don't forget to find a standard error. So, in 7.3, it's read, how to find the probabilities regarding X. Well, today, it's how to find the probabilities regarding X bar. Well, guess what? We now have to have some type of N, a sample size. You can't get an X bar without a bunch of data. The mean of our distribution and the standard deviation of our distribution. So these two are what was given to you in 7.3. Here's the difference. If our X distribution is normal, then the X bar distribution is normal as well. That's huge. So remember, today's dealing with X bar. Even if the X distribution is not normal, if the sample size is 30 or greater, then we can apply the central limit theorem. And basically, the larger that N gets, the more normal it becomes. So that's very powerful. If the data, listen to me carefully, if the data is not really normal, meaning it's skewed, if you find the mean of that data and you keep doing it over and over and find more means and more means and more means and more means, then the means will be normal. Okay, that's the central limit theorem. But there's one small problem. When you're dealing with X bar, your sigma, your standard deviation of all of the means, and that's what that means. Sigma, with this as a subscript, means the standard deviation of all the means. You have to do something to it. You have to divide it by the square root of n. Sigma divided by the square root of n. When you're dealing with X bars. This has a new name. It's called a standard error. It's still a standard deviation, But to distinguish it from a regular sigma, we call it a standard error. Okay? So all this work is still the same. I'm going to give you an x bar. You're going to have a mean. And you're going to have to find a new sigma, i.e. standard error. But everything else, guys, is going to be the same. It's going to be the same. So, if we're dealing with an x bar distribution, knowing that the x distribution is normal, then this is going to be true. The x bar distribution will be normal. The mean of the x bar distribution is still going to be mu. The standard deviation is going to be sigma divided by the square root of n. So all of this I just talked about, but I want to make sure you understand. Okay? The mean will never change. The mean will never change. So this is called the mean of all the x bars. It's the mean of the sample means. Is going to be whatever mu is. So they're going to give you that. This is what you got to remember. This is your standard error. Okay? And then this should look familiar to you. We're going to take a data piece, subtract the mean, divide by the standard error. This example, hopefully, will tell you the difference between 7.3 and 7.4. Or 7.3 and 7.5, excuse me. So let's read. Suppose a team of biologists have been studying the Pinedale Children Fishing Pond that we talked about in 7.4. Let X represent the length of a single trout. Guys, that's 7.3. A single trout is a raw data. That is what you just took your test and quiz on. Taken out at random from the pond. This group of biologists has determined that X is normally distributed with a mean of 10.2 and a standard deviation of 1.4. This is 7.3. They're even telling you right here that it's 7.3. A single fish is raw data. That means we're going to be using the z is equal to x minus mu divided by sigma. Bless you. So here's our question. What is the probability that a single trout, raw data, taken at random from the pond is between 8 and 12 inches? I'm sorry, this should look very, very much like your last test. And here it goes. This is what your tests look like. I gave you this question. So we have to test the 8 first. 8, take away the mean, divided by the standard deviation. It yields negative 1.57. Then we test the 12. 12, take away the mean, divided by the standard deviation, and we round to 2 decimal places and get 1.29. Exactly like the test you just took. Look up the 129, you get 90.15. Look up the negative 157, you get 0.528, and you subtract. And you're done. What does this mean? If I bring my daughter there, and she's 11 years old, and I tell her, you're allowed to catch one fish, because we need to go. We're only going to get one rainbow trout. And she starts fishing. There is an 84.33% chance that the fish, that single fish that she catches, is going to be between 8 and 12 inches. Okay? That is something you already know how to do. Let me show you the difference now between 7.4. We are right here now. New question. What is the probability that the mean length, x bar, of 5 trout? Now I'm doing this. Come on, Caitlin, we're going to go to this lake. You're only allowed to catch and keep 5 fish. So she's going to catch 5 fish. I'm going to add the lengths of those 5 fish together, and I'm going to divide by 5, and that's going to give me the mean length of my daughter's 5 fish. And the question is, what is the chances that that mean length is between 8 and 12 inches? Guys, x bar is not an x. It's a sample mean. This is a new question. This is chapter 7.5 as soon as you see x bar. Well, guess what? The mean of x bar is actually the same as the mean of the x distribution. So 10.2 you don't have to manipulate. We can go as to why, but think about it. If you add a whole bunch of numbers together, 10 of them, and you divide by 10, it's like adding 100 numbers together divided by 100. The mean's going to stay the same. Here's the difference, peeps, right there. The new sigma, which is called a standard error, is to take the original sigma and divide by the square root of n. In this case, it's 5. That'll yield 0.63 as our new divisor. So, notice with this right here, on my very first page I talked about, remember I said x bar greater than, x bar less, and x bar in between? There it is. This is 7.5. So we're going to test our 8, subtract the 10.2, and remember there's our standard error. Not 1.4, 1.4 divided by the square root of 5. Z is in between, there's our 12, testing it with a 6.3 or 0.63 division. This yields a negative 349, this yields a 286. We look up the two numbers, boom, 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 boom on our chart, and this is what we get. So ladies and gentlemen, there is a 99.7% chance, which is a pretty darn good chance, that my daughter Caitlin, when she fishes in that pond and catches 5 rainbow trout, and I add them all together and divide by 5, which is the mean of her trouts, that mean will be between 8 and 12 inches. Okay? That's a pretty good chance. Okay? Pretty good probability. All right? That's the difference between 7.3 and 7.5. This one example is 7.3 at the top and 7.5 at the bottom. Now, I only spoke a little bit about central limit theorem. Is this the central limit theorem? And I'm opening it up to the n. I'll circle him in red. The n was 5. From what I said a little bit ago, is this the central limit theorem? If the n is 5. Anybody remember what the n had to be equal or greater to? 30. So this is not the central limit theorem. But it's still what? Normal. If it's still normal, you can do it. But as this n gets larger, the more normal it gets, and once it hits 30 and more, the central limit theorem takes over, and it says it's going to be normal. All right?